So now that you've had a chance to use a Karnaugh map to take a truth table, convert it to a Boolean expression, a Karnaugh map with 2 variables, we're going to try it with 3 variables and then ultimately 4 variables. So we're going to start with a truth table that contains 3 variables, and then we are going to come up with an answer column. And from this answer column, I'm going to see if I can find the Boolean expression that's generating this using a Karnaugh map. So step number 1, we are going to find the min terms. Remember, the min terms are the terms in the output column that are 1. So we have 1, 2, 3, 4 min terms. This first one right here is x, y, and z. The second one, because x is equal to 1, but y is equal to z, which is equal to 0, this is going to give me x, y naught, z naught. This one will be x naught, y, z. And then this last one down here is x naught, y naught, z. All right, so the second step is to map these to a Karnaugh map. The problem is that now I have 3 variables instead of just 2. So the way that we're going to create this Karnaugh map is, once again, it's going to be like an Excel spreadsheet. But now I'm going to put a single variable down one axis for x. Maybe I'll put the x's here. And then on the second axis, I'm going to group 2 of the variables, y and z. So this first column is going to be y and z. When I move to the next column, it's important to note that I can only change one of the 2 variables at a time. So I am going to toggle y to y naught, and I'm going to leave z the same. And then I am going to leave y the same, and I am going to toggle z. And then finally, I am going to leave z the same and toggle y. So by the time I'm done with this, I should have all 4 combinations of 2 variables, y and z, all 4 possible combinations. But the critically important note here is that we can only toggle 1 variable at a time. So I couldn't go from yz to y naught, z naught. This would not be acceptable. I can only toggle 1 from 1 to a 0 at a time. So we're going to map the min terms to the Karnaugh map. I have 4 1s on my truth table, 4 min terms, and so I'm going to map those 4 1s to my Karnaugh map. This first column right here is in the x row, and it is yz, so that cell should represent where x and yz meet. This one is also in the y row, but it is y naught, z naught, so I'm going to stay in the x row. I'm going to look for y naught, z naught. The next one is in the x naught row where the y and z are meeting. And then the last one is in the x naught row where y naught, z. So now I should have 4 1s on my Karnaugh map. And then we are going to apply our grouping rules. So just to try to remember what my grouping rules were, I have to group 1s in some binary number, 2, 4, 8, 16, 32. I can't group 3 of them, and I can't group 7 of them. I need to group as many 1s as possible using as few rectangles as possible, and I cannot group them horizontally. We're going to see that rectangles can overlap. So let's go back to my Karnaugh map and start grouping. All right, so I need to group as many of them as possible. Would it be a good idea to group all of these since they are sitting beside each other? The answer would be no, because 3 is not a binary value. So I can group these 2 together. This would be an excellent grouping. I'm going to change the color of my pen, draw another group. Can I group these 2 together here? Is that an acceptable grouping? The answer is no, because I cannot group them horizontally. It has to be either vertically or horizontally. Should I group this one all by itself? Well, the answer to that one is no, because the idea is that I need to group as many, as large as possible, and it would seem that since these 2 are sitting together, that I would want to group them with one another. And we did say that overlapping was acceptable. Every single one of them has to be grouped, and since this one is not sitting beside anyone, he's going to have to be a group unto himself. So I'm going to start with the green group here, and then we are going to move through the groups. Step number 3, move through the groups. So if I start with my green group to be as organized as possible, I'm going to move through this group vertically, and we will also move through it horizontally. So vertically just means row to row to row. And since this particular group doesn't change rows at all, it is sitting on the X row. So I will mark that X down as the value that does not change. Remember, we're looking for values in the headers that do not change. And so horizontally, as I move through the group horizontally, I am going to move column to column. Once again, because this particular group does not move through a column, I am just going to write the header for Y naught, Z naught. And that is my green group. Let's do the blue group next. So with the blue group, once again with our blue group, we're going to see if we can move through the group vertically and horizontally. Vertically, once again, with this one, vertically means up and down, and I am not moving, so we are staying in the X naught row. But horizontally now, I'm actually moving between two separate columns, and so I'm going to look for the value in the header that is not changing. I can see between the two columns that we toggle from Y to Y naught, so that value is definitely changing, but the Z remains the Z in both of them, so I am going to put the Z here. This is an implied multiplication, and we'll finish this up with the red group. So again, we are going to vertically and horizontally move through the group. Vertically is top to up and down, and so this time when I move between the rows, I can see that X and X naught, it's toggling, which means that's changing. Now when I move horizontally, that is from column to column, but the red group is only ever in one column, and so the Y and the Z are not changing. And we said that now I have 3 groups. I had 3 values, and I am going to add the 3 of them together, or I should say, or the 3 of them together. So my answer is going to be X, Y naught, Z naught, or X naught, Z, or Y, Z. Now, the nice thing is that this only has 3 terms. If I had done the sum of products over here, we would have had 4 terms. So just by using the Karnaugh map, I have managed to reduce this by 1 term. So let's count up the number of gates that we have in here. So I'm going to say the NOT gates. How many NOT gates are representative in this Boolean expression? I see 1, 2, and 3 NOTs. So how many AND gates do we have? Well, there are 2 here, there's 3 and 4, so I can see that we have 4 AND gates. How many OR gates do we have? The OR gates, there's 1 and there's 2, so I have 2 OR gates for a total of 9. For a total of 9 gates if I were to draw this in a digital circuit. But using our simplification rules, I should actually be able to simplify this a little bit. So I can see that in the second and the third term, they have a Z in common. So I'm just going to factor the Z out. When I factor it out of the middle term, I'm left with Z naught. When I factor it out of the last term, I'm left with a Y, and I'm going to OR those 2 together. So I still have the original Y naught, Z naught. So let's see how many NOT gates I'm left with now. There are 3. How many AND gates do I have now? Well, I can see that there are 2 here and 1 here, so that would be 3. How many OR gates do I have? I can see that there are 2 plus signs. So now I have dropped this down to 8 total gates. But we can actually simplify this even farther, because if I look in this first term right here, I can see that 2 of them have a knot on them. So what I'm going to do is I am going to factor the X out. This is going to leave me with Y naught, Z naught. And then I am going to factor the not out of the y and the z. Now remember, De Morgan's law of negation says that if I factor out the not, it is going to change the logic operator. That is an implied and, an implied multiplication. So when I factor the not out of that, it is going to reverse my logic operator to an or. And then I'm just going to bring down the remaining term. And then we are going to see how many gates that we have. So how many not gates do I have now? Well, I can see that I only have 2 not gates. Here's one and here's one. How many AND gates do I have? Well, there's an AND gate here and an AND gate here, so I have 2 of them. How many OR gates do I have? There are 3 in total. So now I have dropped this down to 7 gates. So the idea is that the Karnaugh map is going to give me a more simplified, can potentially give me a more simplified Boolean expression than the sum of products. But the Boolean expression that it does generate may or may not be the most simplified. So I'm still going to want to apply my simplification rules to take it down to the most simplified that I can. And since we are talking about this particular chapter, that we're trying to go from a truth table to a Boolean expression to a digital circuit, I am actually going to take this simplified Boolean expression that has 7 gates, and we are going to see if we can create a digital circuit for that. So as we've said before, I'm going to draw that. I'm going to transfer it down here, make sure that I get it right and I'm not dropping any knots. All right, let me make sure that I got that one right. So then in order to draw a digital circuit, we've decided that I want to do the very last operation first. We're going to start on the far right and work our way backwards through a digital circuit. So the last operation that's going to be performed is this OR. And the OR is going to be ORing 2 terms together. And so I'm going to draw an OR way over here on the far right. And what is coming out of that is the first term ORed with the second term. And OR operators are binary. They need 2 input values. So the first term, term number 1, is going to be x, y plus z not. Let me make sure that that not is on the outside. The other term that is coming into that OR is x naught or y and z. So I'm just going to take the top track, this one right here. What is the very last operation that is being performed here? Well, it seems to me that I am ANDing an x with some other term, so I'm going to draw an AND gate. And there are 2 terms that are coming out of the AND gate. The first term is an x. The second term is a y or z not. Very good. I'm just going to draw this x. Oops. I'm just going to draw this x out here, and then the input on the x is going to be here. So now let's look at the term here, the y or z not. What is the last operation that is occurring here? It seems like I am knotting something. So I'm going to put the not symbol here. There is a single thing that comes into a not gate, and that would be a y or z. My y looks more like an x than it does a z. All right, that's a little bit better. Y or z. So what is the last operation that is occurring here? That would have to be an OR. So there is 2 values that are coming into an OR. There is a y and a z. Let me draw that a little bit differently. There are 2 inputs that are coming out. There is a y coming out and there is a z. And so I'm just going to drag these back across this line here so that I have the y and the z. Now we have looked at the top part of this equation, which was the first term. So now what we need to do is repeat the process for the second term. So if I look at the second term right here, what is the last thing that's going to occur? Well, I can see that multiplication. I'm going to drag this down just a little bit to give myself a little bit more room. So that is an AND operation that has 2 values that are coming into it. One of the values coming in is a z, and one of the values is an x naught or y. X naught or y. So the z I am going to just bring this straight across up here, oops, and connect it to the z that already exists. This term, the x naught or y, it looks like the very last operation that's being performed is this or. So I am going to draw. My drawing is deteriorating rapidly. All right, that might be a little bit better. There are two terms that are coming into this one. There is an x naught and there is a y. I'm going to deal with the x naught first because we're going to have to pass that through a NOT gate. This y, on the other hand, does not have to pass through a gate. So what I need to do is I need to manage to connect this x all the way up here. This might be a little bit tricky because apparently I am horizontally challenged. I'm going to draw it all the way up here and connect it here. And then the y, I also have to take the y all the way up there and connect it to the y. It might be a little bit easier to do if I erase that original line so that I can bring my y up here. We're going to have to jump over the z and attach to the y. It's more difficult than I would imagine to draw a straight line, straight horizontal line on a iPad. All right, so barring all the squiggly lines, I now have a digital circuit diagram that is mapping that Boolean expression. And as we have already tried, I should be able to take any one of the x, y, and z input values, put it through my digital circuit, and generate an outcome. Let's say, for instance, that I were to pick this particular row right here, which has an x value of 1, a y value of 0, and a z value of 0. I should be able to put a 1, a 0, and a 0 across this through my rather scattered digital circuit diagram, and it should come out to a 1 on the other end. So remember that when I'm doing this, I need a single x, y, and z. It would have been so much easier when I was doing my second term at the bottom of this diagram if I could have just dragged them out straight horizontally and had another set of x, y, and z instead of having to jump them all the way up to the original 3 x, y, and z. But the way this diagram works is there are only 3 input values that are generating a single output value. All right, so there's a couple of things I want us to consider when we are mapping minterms and grouping minterms on a three-variable Karnaugh. So here I've drawn a 3-variable Karnaugh map, and I'm just going to put, let's say that my minterms were mapping to these 5 cells on the Karnaugh map. So we've already said that I should be able to group as many as possible. I see those 2. We also said that overlapping is acceptable. So now I see a minterm or one that is a part of 2 groups. But then you might say to yourself, can I just put this one as a group and this one as a group? But one of the rules said that I can actually wrap around the edges. So what we're going to find out is if I had ordered my Karnaugh map any differently, these 2 ones may have been sitting side by side. So I'm actually going to group these 2 and wrap around the edges. So what would happen if I had actually ordered my columns and rows differently? What happens if I had started with the YZ here, and then I toggled the Y and left the Z, and then I left the Y and toggled the Z, and then finally I toggled the Y and left the Z. So this is a new ordering. I've actually just shifted everything 1 to the left, which means that when I put my 1s here and here, I have shifted everything to the left. And it means that this one is going to shift to the left. And it means this one is actually going to shift over to the first column. So now I can see that if I had ordered these differently, these 2 actually would be sitting side by side. That's the reason why we can wrap around the edges. All right, so here's another example of a Karnaugh map. And if I'm grouping, I can obviously see the 4 of them together. I'm definitely going to want to put that as a group. But everything inside of my brain is telling me that I am going to have a group of 2 here, and then I'm going to have another group of 2 here. But we have already seen that I can wrap around the edges, and I need to have as large of groups as possible. And so I'm actually going to group these 4 into a single group. Now I only have 2. Before that I had 3 groups, which is going to potentially be 3 terms in my Boolean expression when I'm done with it. And just by grouping the 4 on the outside edges, I have now dropped this down to 2 terms when I find my Boolean expression. Alright, so now I find myself with this Karnaugh map down here at the bottom, and we're still talking about wrapping. So my brain wants to wrap the top 3 together. The only problem with that is that I cannot group 3. Remember, it has to be some binary multiple, and 3 is not a binary multiple. 1, 2, 4, 8, 16, 32. So I cannot group those 3 together. So instead, I can group 2 of them, so I'm going to group these 2. We said that every one needs to be grouped. Should I just group this one down here all by himself? We said the groups had to be as large as possible, so I'm going to group him with this one. That gives me 2 of them. Excellent, but I still have 1 down here. And I'm going to group this one all by himself. Once again, we need as large as groups as possible, which means that I am going to group this one with the one immediately above him, which means that the one in the center top is actually in 3 separate groups. And that is acceptable. We said that overlap is acceptable. So we're going to give you a chance to do a 3-variable Karnaugh map. Your turn. Turn to page 263 in your book, the international version. That should be on page 293. And I want you to do number 3. They are going to give you a truth table, and from there I want you to draw a Karnaugh map, and from there I want you to generate the Boolean expression. So you're going to take the truth table to a Karnaugh map, and from that Karnaugh map I want you to show me the Boolean expression. And then we can actually, from the Boolean expression, we're going to take it to a digital circuit. So we will have the 3 representations: the truth table, the Boolean expression, and the digital circuit for the truth table they gave you in number 3. Alright, so now we're going to try our hand at 4-variable Karnaugh maps. If I have Boolean variables and I have 4 of them, this should give me 16 rows in my truth table. So I'm going to draw the 16 original rows and the output column. Alright, so also horizontally and vertically challenged, but because I'm going to have 16 rows, I'm going to toggle the X 8 ones and then 8 zeros. I'll toggle the Y 4, 4, 4, and 4. Then I'll toggle the Z 2 and 2. And then finally I'll toggle the W 1 at a time. So I'm going to group them by 4s, draw a line, the horizontal line between the 4s, just so I can try to keep this one straight. And then I'm going to draw the output column. So as always, the first thing that I'm going to do is find the min terms. There are 8 min terms here. I can see that there is 1, 2, 3, 4, 5, 6, 7, 8 ones in the output column. So I'm going to find the min terms that are generating those. This would be X, Y, Z, and W naught, because I can see a 0 in the W column. This is X, Y, Z naught, W naught. This one right here is going to be X, Y naught, Z, W naught. This one is going to be X, Y naught, Z naught, W naught. The last 4, this is X naught, Y, Z, W naught. This one, make sure I get the right one, is X naught, Y, Z naught, W. Gotta make sure I get that one right. This one is X naught, Y naught, Z, W naught. And then this one is X naught, Y naught, Z naught, W. Let me double check those. Alright, that seems to be good. The next thing that we're going to do is we are going to map the min terms to the Karnaugh map. Now I have 4 variables. So what I'm going to do is I'm going to draw a Karnaugh map that has 2 of the variables grouped on each one of the individual axes. So I'm going to group the X and the Y along one axis. Let's toggle the X and leave the Y. I'm going to leave the X and toggle the Y. Then I'm going to leave the Y and toggle the X, and hopefully I have all four combinations of two variables. I'll do the same thing across the top. We are going to start with ZW. I'll toggle the Z and leave the W. I'll leave the Z and toggle the W. I'll leave the W and toggle the Z. Now again, it's important that I only toggle one variable at a time. So then what I'm going to do is I'm going to map the min terms. So this is in the XY column or row, and this is the XY row. I'm looking for ZW0, that will be here. I'm looking for the Z0 W0, which is going to be here. In the XY0 row, right here, this is the XY0 row, I'm looking for ZW0, which should be right here. And then I'm looking for Z0 W0, which should be right here. In the next row, this is going to be X0 Y, which is right there, X0 Y. I'm looking for the ZW0, which is there, and then I'm also looking for the Z0 W, which should be here. Then we have two more to do. This is in the X0 Y0 row, which is here. I'm looking for the Z W0, which is here, and then I'm looking for the last one, which is Z0 W, right there. So I have 8 min terms. I should have 8 ones in my Karnaugh map. So the next step in the process is to group the min terms. So we're going to group them following the rules that we know of. I'll use some different colors because the first thing that I see is these four all together. I'm going to call that one the black group. Then we're going to look for a red group. I see these two together, which would be nicely a red group. And then I'm going to have a green group. All right, so in my green group, should I put these separate and apart? Or would it be better for me to group them together since they are, I can wrap top and bottom just like I can wrap side to side. So I'm going to remove those and I'm going to actually group these two together here and here. But as we said before, the idea is to group as many together as possible. And even though the green group is wrapped top and bottom, I can actually see that the green group should include the two that are beside it because the rules say to group as large as possible. And so I have 4 ones sitting together when I'm wrapping top and bottom. So now I have a green group, a red group, and a black group. So the next step is to move through the groups. I'm going to have to put this step up here because I just ran out of room. So we're going to start with the green group as we move through. So to be organized, we're going to move through it vertically and then we're going to move through it horizontally. In the green group vertically, that means that I'm going to go from row to row. Well, I could see that the green group is going from this row to this row. Maybe I should draw it over here because the row headers are over here. And as I move to each one of those 2 rows, I can see that the only value that is staying the same is the X. And then I'm going to move through the group horizontally. That's going to take me from column to column, and the only value that is staying the same here is W0. So let's do the red group next. So the red group, once again, vertically and horizontally. The vertical is pretty easy, or excuse me, the horizontal is pretty easy because it never moves out of the row. So this is going to be a ZW0. The vertical, on the other hand, is moving between these 2 rows, and I can see that the value that is not changing is the X0. So let's do the black group last. So in the black group, we have the 4 ones on the very final column. Once again, if I go vertically and horizontally through it, horizontally is pretty easy because it never moves out of that particular column. So that would be a ZW0. Vertically, on the other hand, is actually moving between all 4 of the rows. That begs the question, is there any value that is not changing? And the answer is no. Both the X's and the Y's are changing, which means that there is nothing to multiply that by. So what I'm going to do is OR these 3 terms together, and I get an XY0 or X0 Z0 W or Z, W naught. Let me check, make sure that I didn't drop any of my knots. Okay, this looks pretty good. So then let's count up gates. How many not gates do I have? 1, 2, 3, 4. I can see 4 tick marks. How many and gates do I have? That's implied multiplication. 1, 2, 3, 4. And how many or gates? That is addition. I see that there are 2. So I have a total of 10 gates here. But can I actually reduce this down by simplifying? Remember, the Boolean Karnaugh map is not always going to generate, not usually going to generate the most simplified. So is there a way that I can simplify these terms? Well, it seems like this term and this term both have a W naught in it. So I should be able to factor out the W naught from those two terms, which leaves me this X Z naught W. But I can see that there are knots in both of these, which means that I should be able to factor out the X and the Z naught. I still have to have it multiplied by that W, and when I factor the naught out of the X and Z, it is going to reverse that logic operator. So let me drop this down, X plus Z naught. Oh, excuse me. That's going to be X plus Z. Now we're going to count up the number of gates that this particular Boolean expression has. How many not gates? I actually only see 2 not gates. How many and gates do we have? That's implied multiplication. Well, we are multiplying here and here, so that is also 2 gates. How many or gates do we have? I'm looking for plus. 1, 2, and 3 plus signs. So that is 7. So just with a little bit of simplification, I went from 10 gates to 7. So here's another example of one that I have worked out a bit. This one is similar to the first one, but a little bit different. I have 8, once again, I have 8 min terms in the output columns. I have mapped each one of those min terms to the Karnaugh map, but I can see on the Karnaugh map the grouping looks a little bit differently. So the next thing, once I have mapped the min terms to the Karnaugh map, the next thing that we want to do is we want to group them. So how am I going to go about grouping these? I'm going to start my first group in red. These seem to be all over the place, but the first thing that I see is these 2 that are sitting together. And I actually see these 2 that are sitting below it. So I'm going to group the 4 of those together, and then we'll move to another color. How about if we do a blue group? So I'm going to pick these 2 up as a blue group, and I'm trying to see if there anybody else that's around it, and I don't see that. So then we're going to do a green group next. So I'm going to group these 2 together as a green group, but I still have these last 2. I don't see wrapping top to bottom. I don't see wrapping side to side. So those 2 are going to have to be groups of their own because I cannot group diagonally. All right, so I see that we have 5 groups. I'm going to start with my purple group first. If I move vertically and horizontally through it, I can see that because it's not going anywhere, that I'm just going to have the row value along with the column value. Then I'm going to move to my black group next. The black group is also going to be just the min term that generated it. I have my row value and my column value, if I got that right. Then we're going to do the green group next. So in the green group, there is actually more than one. So even though I'm going to keep, when I move through it vertically, I am going to keep the Y naught, excuse me, the Z naught W naught. But when I move through it from row to row to row, I'm actually going to be keeping the one value that does not change, which is the Y naught. And then we'll do the blue group next. So in the blue group, I'm seeing that I'm keeping the ZW naught, but as I move from row to row, we are keeping the Y. And the last one is going to be the red group. Now the red group, I'm going to move through it. Let's try moving through it vertically first. When I move through it vertically, that is going to go from this row to this row. So I'm looking at the values of X and Y here and here. I can see that the X is staying the same, so I'm going to keep the X. Now I'm going to move through it horizontally. That means that this group is spanning 2 columns. When I look at the column headers, I see that the Z is changing, but the W naught is not. So I'm going to leave that as a W naught. and then ultimately I am going to OR all of these terms together. So I rewrote those together right down here because ultimately I'm probably going to try to do some kind of a simplification process. I want you to notice that the blue group was the largest, and the blue group was the one that managed to sift out or simplify out 2 of the 4 variables. The ones that I were not able to group at all had the original 4 input values in the minterms. When I was able to group them at least a little bit, I was able to filter out or simplify out 1 of the 4 variables. This is the value of a Karnaugh map. And I have a variety of different ways that I can simplify this down. I see that this term, and this term all have a W0, so it seems like I'd factor out the W0. I can see that we have an X0, Y0 here, and oh, that's the only one with the X0, Y0. So I'm looking for commonalities. There is a Z0 here and a Z0 here. Maybe I could factor the Z0 out of those. There are a variety of different Boolean expressions that I could ultimately come up with depending upon the way that I simplified this particular Boolean expression. All right, so I'm going to give you a chance to do your own 4-variable Karnaugh map. Once again, we're still on page 263. The international version is page 293. This time I want you to do number 5. So you're going to start with a truth table. From there you can generate, I'll just have it generate the Boolean expression. We're going to be using the Kmap or the Karnaugh map to generate that Boolean expression, and then I want you to simplify it. So let me tell you what our confidence is for today. I'm going to draw it up here at the top. The first thing that we started talking about was min terms. After that we discussed the sum of products, and then I'm going to have to drop down through here. Then we introduced the idea of a Kmap. And we had 2 variable, oops, that looks like war, 3 variable, and also 4 variable Karnaugh maps. I would like to know how your thoughts on grouping and the rules that we apply when you are grouping the ones in a Karnaugh map. And then finally, your thoughts on or your confidence on simplification. So that is the end of 6.6. Submit your turn as your classwork for 6.6, and I will give you credit for it.